So thank you for your kind introduction. So I'm Monterubbiano. I'm a PhD student from University of Rome, Sapienza. Today I'm gonna present this paper, SPADA. It stands for Sparse Approximate Data Structure Representation for Data Plane for Per Flow Monitoring. This paper is the result of a collaboration between University of Rome, Sapienza, and researchers from Huawei Research Lab here in Paris. So let's first introduce the problem. We are talking about per flow monitoring. So many network measurement tasks require to collect per flow statistics. Usually a flow can be identified by its TCP/IP5 tuple. So source IP, destination IP, source port, destination port, and protocol number. There are many use cases where we need to collect per flow statistics like flow cardinality estimation, flow frequency estimation, and the estimation of the distribution of some flow metrics. So from recent literature, what we found that there are about 120K flows for each additional gigabit of network traffic. So for modern network switches that can process data in the order of terabits per second, if we want just to store a flow identifier plus 4 bytes counter to estimate the flow size, this adds up to having more memory, to require memory in the order of gigabytes, and this is unfeasible for modern network devices. So in what we use approximated data structure to perform these tasks. Our claim is that also this data structure are sparse in the sense that I will explain shortly, and their memory footprint can be optimized. So we work on 3 use cases, on 3 data structure: the hyperlog log for cardinality estimation, the distributed distribution sketch for quantile estimation, and elastic sketch for frequency estimation. Just introduce the second data structure, the DD sketch. So this data structure is used to estimate quantiles for distribution of values. So the range of values is divided into bins that are with sizes exponentially increasing. So whenever a new sample of the distribution arrives, it is just mapped to its corresponding bin. This bucket just acts as a counter, and it is increased. So whenever we need to compute a quantile for the distribution, we just compute the corresponding rank. We found in which bin this rank falls, and then give an estimate based on the delimiters of the bin. In our case, we monitor the distribution of the inter-arrival times of network flows. So we have a DD sketch for a single for each network flow. So when having multiple flows, we just have a set, an array of DD sketches. We can imagine to put all these counters in a matrix where we have 1 row per each flow. And as you can see, actually, most of the counters of the DD sketch are left unused. So we have a sparsity both in the rows and in the columns. This is true also for the other use cases we worked on. Here there's a list, a table with some other data structure for which we can apply SPADA, so data structure that entails this array of counters or bins. So we have this sparse matrix. There exists in literature many ways so there's a huge literature how to deal with sparse matrices and how to efficiently represent these matrices. One is through recent coordinate format. So we have three arrays, one for the non-zero values of the matrices, and the other pointing to the row index and the column index of these values, and also other techniques related to machine learning and deep learning, where matrix calculus is a pivotal importance. But the issue with these existing techniques is that they're not feasible. It's not easy to implement in network programmable network devices, both from a memory perspective, but also from the computation point of view, because this representation requires some computation overhead to actually identify a matrix value, and this is not feasible in modern fast packet processing pipeline when we want to be fast to keep up with the network data rate. So take-home message is that this per flow monitoring data structure are sparse. So we propose a way to efficiently exploit this sparsity, so to reduce the memory footprint, and in a way that is compliant with the modern programmable network devices. So let's introduce our system, the design of our system. So SPADA is composed of two main blocks, the flow map and the sketch data. So this first block, the flow map, whenever a new packet is received, the flow key is extracted, for instance, so the 5 tuple, and this flow key is passed as input to the flow map. The flow map keeps track of the monitored network flows and just assign to each flow key a sketch identifier. Then this sketch identifier is used in the second part of SPADA, this sketch data block, and just points to the related counters for that flow. So let's talk about the baseline, our baseline system. So for the flow map can be implemented in many ways. For instance, through match action table that are omnipresent in modern networking devices. So it is a responsibility of the control plane to populate this match action table with flow key sketch identifier pairs. Another possibility is to use a Kuko hash table. So in this way, we can dynamically insert new flows in the flow map as they are seen in a network trace. So whenever a new flow arrives, it is assigned a sketch ID taken from a counter that counts how many flows we have seen, and this new pair is inserted into the Kuko hash table. As you can see from the animation, inserting Kuko hash table is actually composed of many tables where keys can be moved around, and so while being efficient, it is not so easy to implement it in hardware. For the sketch data part, instead, the baseline implementation is just, as I said before, an array of sketches. So we have this matrix of counters. Each row corresponds to the counters of the buckets for a specific sketch for a given flow. And so the sketch identifier just points to just an index in this array. So as I said, it is a sketch array section. Many of the counters are going to be 0, so are going to be left unused. What we want to do is just instead substitute this sketch array with a data structure where we save only the non-zero counters and non-zero buckets. So we need a key value data structure where the identifying key is composed of the sketch identifier plus the index of a non-zero bucket. We propose two solutions, so based on two different data structures. One is this cuckoo hash table that I'm going to present, and the other is the PIBLT, a novel data structure that we crafted for this purpose. So I'm going to show just the cuckoo hash table version. So this is just a normal cuckoo hash table, but it also exploits this quotient technique in order to save some space in key storage. So whenever a new key value pair is to be inserted, the key is first hashed through a bijective hash function. So the first bits of this output hash are used as an index into the tables to point to a specific row of the table. And we use as the key, as the fingerprint that is stored in the table, the remaining bits. So in this way, we save some space in with respect to key storage. And the value stored in this table is just the value of a non-zero counter. So instead, the PIBLT doesn't require key movements. So in this sense, it's easier to implement, but it needs some post-measure decoding in order to retrieve the actual value of the counters. So let's talk about the implementation of our system. We implemented the SPADA and FPGA smart networking interface from Xilinx. We exploited also a P4 framework offered by Xilinx. And I want to focus on the cuckoo hash table implementation. So instead of using just one table for the sketch data part, we use many parallel tables. And in this way, so the load is split between these parallel data paths. Moreover, each cuckoo hash table has a stash, so it's additional memory. So whenever a new key can't be inserted into the table, instead of starting this key movement process immediately, it is first inserted into the stash. When all the stashes of the different data paths reach a certain load factor, so certain threshold, at this point, recirculation is started. So what we want to do in this way with multiple data paths is to recirculate more than one key at a time. And so in this way, we want to reduce the overall amount of recirculation needed to populate the table. So briefly, through the resource utilization for the FPGA, we inserted SPADA inside the NetFPGA project. We have a small overhead with respect to the original project. Moreover, we also checked that also with the actual implementation using cuckoo hash table and PIBLT, we save resources with respect to the baseline sketch array implementation. So also evaluated the SPADA in simulation in some experiments on the three use cases, three data structure I introduced at the beginning. So the Hyperlog log, the DD sketch, and the Elastic sketch. Our simulation data set is composed of three CAIDA traces. So we evaluated different configuration in terms of number of buckets for this different data structure. So at first, what we did is compute the sparsity on the baseline implementation, then compute what the memory saving we could obtain using SPADA, and also we evaluated the recirculation overhead introduced by employing the CoCoH table. Here are some results. So we can reduce the memory footprint of the sketch data part up to 13 times. This is using for the hyperlog configuration with 128 buckets per flow. So this is using as a sparsity value the maximum, the optimal sparsity value. Using also say conservative values, we can also obtain memory reduction. Moreover, what's interesting for the SPADA elastic sketch use cases, where there's a CMS count mean sketch involved, using the same memory as in the original paper, what we obtained that with our system we can represent a larger count mean sketch, and so obtain better performances in terms of accuracy for the flow size estimation. For what regards recirculation overhead, so we evaluated this recirculation overhead in terms of recirculation rate, that is the ratio between recirculation packets and the overall amount of network packets. In fact, recirculation is implemented by crafting artificial packets that are inserted at the beginning of the processing pipeline. So in this way, we have this kind of network overhead, these additional packets that should be processed along with the normal network packets. You can see from the image on the left that using more than one data path, so the yellow line, the green line, this average recirculation rate is reduced as the load factor of the CoCoH table increases. We also evaluated the latency introduced by our system. This was done on the real FPGA prototype. So as you can see in the image on the left, as the load factor of the CoCoH table increases, the latency introduced by our system increases. This is not true for using multiple data paths. So as you can see in the image on the right, just using 2 data paths, the latency is not affected by the increasing load factor of the CoCoH table. Okay, so let's go to the conclusion. So with our work, we show that per flow measurement data structure are sparse. There are specific techniques that can be applied to exploit this sparsity. So with SPADA, we propose to use 2 data structure, this CoCoH table and this novel data structure called PIBLT. And so with a limited overhead, we end up with a huge memory saving, and also in the case of SPADA, elastic sketch will increase the accuracy of the estimation task. So thank you for listening to me.
We still have some time for questions. Anybody wants to ask a question? Well, let me start maybe with a quick one. So nowadays, when people talk about programmable networks, they think about Tafino switches. You did it on FPGA.
Yeah.
So why?
But on FPGA, this recirculation mechanism in some sense is easier to implement, to be implemented. So
very nice presentation. One simple question. This is you think as a device that like a network traffic is mirrored into it, or like as a switch, as Sergey was suggesting? Because I mean, both are possible. One is on path, and the other one is off path.
So didn't understand the first network graphic.
No, like kind of if you you can imagine this is in a machine that is collecting traffic, or like on path.
Okay.
So they are different. Like a Tofino wouldn't, I think, make sense.
Okay, but it's kind of that's how we implemented the actually on a so a smart NIC that's placed on an NDOS system. I mean, as I was saying, in implementation on a Tofino switches, due to the limitation of the memory model, as won't be so simple in this way. But of course, listen, you have the match action table, so you have some structure to implement kind of this system.
Thank you.
Just to give it time to others to think. Another short, maybe provocative question. So I didn't see any ACM badges next to your paper. So I guess you didn't apply for artifacts.
Yeah.
So it's another question, why? Right? Is that Huawei policy? They're going to use in products, or it's, I don't know, maybe waste of time for the student?
No, the prototype, the code. I have the code of the prototype. Okay, it's up to also Huawei. I don't know. It's not a question I want to discuss.
Okay. Thank you for the honest answer. So,
code is open source. It's open source.
So thank you for the introduction. So this work was jointly done with Oliver Gasser at the MPI. So then, without waiting any further, let's dive straight in. So let's first start at the old internet, the traditional internet. The traditional internet paints a very simplistic picture of the internet, because it envisions that the more complex tasks will be done at the endpoints of the communication, whereas more simpler tasks, which involve obviously packet forwarding and routing, they will then be handled in the middle of the network at obviously routers. But then these are obviously textbook descriptions, and these are no longer valid now. This is because the internet now is far more complex than it was when it was first designed. And a good example of this increased internet complexity are devices called Middleboxes. Now, these devices sit in the middle of the internet and perform tasks which, well, are not permitted by these traditional definitions. Now, in fact, these have been found to perform other tasks, for example, inspect, filter, modify, and even drop packets. And while today they are deployed for more benign ends, some of them are deployed for benign ends, such as address-space expansions, balancing of resources, and prevention of attacks. Some of these also entail dangerous side effects. And one such dangerous side effect is the ossification of the internet. Now, this means that these simply sit sort of in the way of new protocols, or even extensions to existing protocols. Now, in this work, we focus on the latter. We look at more specifically packet rewriting Middleboxes. We look at how they interfere with internet traffic at the IP and the transport layer. So the Middleboxes that we're interested here are legacy devices. These could also be misconfigurations, and these could also be Middleboxes which were sort of benign in the past, but now they tend to break paths. And in this work, we are also interested in sort of identifying the positioning of these devices in the internet. And in doing this, we hope to improve upon existing tools and make internet scale Middlebox detection feasible for the first time. Now, I already very briefly motivated the need to study these devices, but I'll try to do this here in a bit more detail. So as I mentioned, these devices have a negative impact on the evolvability of the internet. A good example of this are, again, protocols such as TCP and SCTP. Now, despite having been standardized for quite a while, they still fail to be deployed at scale. This is because Middleboxes treat these as unknown or foreign protocols and drop traffic that carries these. This then means that protocol designers and researchers have to find very creative ways to produce innovation, and they have to ensure a sort of Middlebox proofness of their solutions. Now, in this work, we acknowledge that these devices are here to stay. They are an internet reality. So we must then have a good understanding of their behaviors so that we can then work around them. In addition, some of these devices have been seen to not always be on all the time, but they tend to exhibit transient dynamics. And this then means that not only do we need to detect them at an internet scale and study their behaviors, but we also need to do this in a timely fashion. And these are the goals that we set for ourselves in this work. So there are several approaches which I've looked at identifying Middleboxes in the internet. One very promising approach is based on traceroute. It's what is practiced by a tool called Yarrpbox. Because the approach is very similar to the working of our tool, I'll try to spend a couple of minutes here to explain how it works. So on the left-hand side, then we have a client which runs Yarrpbox, which runs this style of detection. And in this case, this style of detection is being run towards the server, towards on the right-hand side, towards its IP address. Along the path, we also have 4 routers, or hops as they're called. And between the first and the second hop router, there's a middle box which is altering the TCP header, where it's changing the TCP sequence number. So then, in order to detect interferences to these packets, Yarrpbox will craft such packets. They'll have an IP header and a TCP header, and this is what it will look like. But before the packet is being sent out, it will have a TTL assigned to it. As you probably know, TTL is just a field within the IP header, which ensures that the packet is not traversing forever in the internet. So before sending out a packet, a TTL is assigned to it, and then every hop along the path will decrement the TTL by 1. And in case the TTL is not large enough for the packet to reach the destination, the packet will be dropped, and a diagnostic message will also be sent back to the original sender, basically telling the sender that the packet didn't have a large enough TTL for it to be carried across to the destination. Then this diagnostic message also carries a copy of the original packet, a quotation of sorts. And this is basically like a snapshot of what the router sees, which is sending this message. And it is this snapshot, this particular quotation, this copy of the packet that Yarrpbox and later also us used to basically study Middlebox interferences to packets. So then going back to the example, Yarrpbox then sends these packets with an increasing TTL. So the first packet is sent with a TTL equal to 1. It only goes until the first hop where the TTL is decremented to 0 and the packet is dropped and a diagnostic message is sent back. Then the next packet will be sent with a TTL equal to 2, which will go past the first hop, then through the middle box over to the second hop where the TTL will again be decremented to 0. But this time, more importantly, it will also have an interference applied to it. And again, then packet is dropped and diagnostic message again being sent back. So this is what this diagnostic message looks like. It's an ICMP time exceeded response. This is the header format, the IP being the IP of the routers, which are sending this diagnostic message. As I mentioned, it also has a copy, a quotation of the original packet. So this then means that the Yarrpbox running client on the left-hand side has a snapshot of the packet as seen at the second hop router in that example. But it also keeps a copy of the original packet. And then Yarrpbox can then simply perform a field-by-field comparison to basically detect where the interference, what interference has taken place. Now, all this is very nice, but then Yarrpbox and this style of detection doesn't really come without its limitations. The major issue with this style of detection is that it maintains state, and Yarrpbox maintains state over outstanding probes. In fact, it sends the next probe only after the response to the previous one has been received. This obviously makes the tool quite slow. And additionally, the tool is also sequential in its nature, which means that it probes all hops along the path in sequence. This obviously then has the effect of concentrating load across paths, links, and routers, and has the potential to trigger ICMP rate limiting. Now, this ICMP rate limiting means that these diagnostic messages, which are so central to detecting these devices that we're so interested in, will then not be sent as frequently. And also, this ICMP rate limiting is far more aggressive in IPv6 than in IPv4. So this means then all of these factors then mean that Yarrpbox is not the most ideal candidate for studying Middleboxes at an internet scale. The question that we ask ourselves here is that can we do better? And we believe that we can, and this is where we propose our tool Yarrpbox. So we basically build Yarrpbox on top of another. Instead of building it on top of traceroute, we build it on top of a different network topology mapper called Yarrp. The major distinction that Yarrp has to traceroute is that it allows for probing at very high speeds. By building the tool on top of Yarrpbox, we already make several improvements over Tracebox. First of these is the randomized probing of the tool. And this probing is randomized over the IP and the TTL domain, which means that instead of probing all hops towards a target T1 in sequence, we can pick a particular hop towards T1, then another towards T2 and T3, and in this way sort of basically spread the load across different paths. This then has the potential to minimize ICMP rate limiting. Also, the tool is stateless in its operation, which means that it's fire and forget in its nature. So we are not basically waiting on previous replies before sending out the next probes. We just simply fire away the packets. Now, this is possible because we encode the state information into the outgoing probes themselves. For example, on the right-hand side, we have an IPv6 packet, and we encode the payload information here in the payload of the packet. The state information obviously includes the target IP that we're targeting and the originating TTL with which the packet is being sent out. Once we get the responses from the network, we extract the diagnostic messages. When we extract the state information from the quotation in the diagnostic message, and then basically we reconstruct paths and apply the middle box detection logic similar to how our Tracebox does. And it is these major tweaks that we make here that make the tool feasible for large-scale, internet-scale middle box detection studies. So in terms of the features of the tool, then, the tool builds middle box detection of the sort that is performed by Tracebox into Yarp, and that already results into a stateless high-speed load distributive middle box detector. The tool can detect interferences without any support from the target, and it can also give us an approximate location of middle boxes in the IPv4 and the IPv6 internet. Although we make improvements over Tracebox, but there are certain limitations to the tool. Firstly, we cannot detect modifications to all the fields from the headers. This is especially true for the fields that carry state information, because these fields are dynamic in nature. But this is something which is true for a couple of header fields from the IPv4 packet, because as I mentioned, for IPv6, we encode the information into the payload. Additionally, the location that we detect will, in most cases, only be approximate for the middle boxes. And this is not an inherent limitation of our tool, but this is something that will exist with most traced out-based methodologies. Then enough with the technical details. Let's look at a couple of results. So in terms of the contributions that we make in the study, we performed the very first internet scale IPv4 middle box study till date. We probe a single random IP address from each/24. For IPv6, we performed the very first middle box detection study. And we use BGP announced prefixes, where we probe 100 IPs per prefix. Finally, we also perform measurements from geographically distributed vantage points. We run our scans from 8 different vantage points located across 6 different continents. And this gives us a more diverse picture of middle box deployments in the internet. And we estimate that the measurements that we perform with our tool, if we did these with Tracebox, they'll take in excess of 58 years. With our tool, we do these in under 10 hours. So then here is an example of running Yarrpbox to a particular target, in this case to 8.8.4. This is a trace. The first column is the hop numbers. Then we have all the route interfaces. And finally, any middle box interferences that the tool is able to uncover. So although I showed the middle box to be present between 2 routers, the middle boxes that we're interested in are mostly our implementations on routers. And we identify them based on the hop numbers and the route interfaces. So then again, going back to the example, now if you look carefully at the trace, we'll find that the 4th hop is missing. Now this is something which is quite common in the internet. Some routers, some devices on path are not simply configured to send these time exceeded responses. This then means that there's a gap in our trace. And this gap sort of creates an uncertainty for us, because we cannot now say for sure that the interference happens at the 5th hop. It could easily have also happened at the 4th hop. So this means then to detect middle boxes accurately, we need traces that are complete or compact, or in the worst case, for the gaps to be as small as possible. So now we look at the state of the traces that we collect with our tool. Here are the results for our IPv4 TCP SYN and IPv6 TCP SYN scans. We also perform UDP and ICMPv6 scans because the distributions look quite similar. We go with these here. Y-axis has a fraction of all traces. The x-axis has the gap sizes. And the most desired gap size for us is a gap size of 1. Now, this is the desired size because it's sort of the minimum possible gap size, because at a minimum, the hop numbers increase by 1. So in the blue, we have the results for V4. In the orange, we have the results for IPv6. And we find that nearly 40% of our IPv4 traces are complete. And for IPv6, nearly 60% of the traces are either complete or the largest gap therein is a gap of 2. So these results basically demonstrate that this load distributed and randomized approach to probing is working out quite well in the wild. And this is what we also see in how accurately we are able to detect middle boxes. So here we try to classify these potential middle box IPs into different sets of higher and lower confidence. A potential middle box IP being like hop number 5 was in the previous case. So along the y-axis, then we have the fraction of all traces, fraction of potential middle box IPs. Horizontally, we have different sets based on these gap sizes. The most desired set is a set with a gap size of 1. That is the highest confidence set. So this set will have potential middle box IPs where the previous hop just before the middle box hop replies. So we are quite certain in this being the middle box hop. So on the left, we have IPv4 results, on the right, IPv6. For both, we find that the majority of the middle boxes map to the highest confidence set. This then again goes to show that the tool is able to detect middle boxes quite accurately in the internet. Then we stick with these highest confidence middle box IPs. We map them to their ASs and look at the interferences that are happening in the top 5 ASs. Now, vertically, we have, firstly, these are results for IPv6 TCP SYN scans again. Vertically, we have the top 5 ASs, the AS numbers. Horizontally, we have any interferences that they perform with packets from the IP and the TCP header. And as you can see, all 5 of the top 5 ASs predominantly alter the TCP checksum. TCP checksum, as you probably know, is a field from the TCP header, which is sort of like an integrity check over the header. So it's computed over several fields from the IP header and the TCP header, pseudo header, the payload. So firstly, the field has an end-to-end significance, so it should not be altered. But if it is altered, these alterations should come from modifications elsewhere in the header. To our surprise, we find that there are several instances where the field is solely altered. In fact, in 3 out of these 5 ASs, we find the checksum to be predominantly zeroed. Now, this is quite alarming because once the checksum is incorrectly computed, the packets will be dropped. And this is what we notice from a manual inspection into the traces as well. Finally, instead of just looking at the top 5 IPv6 ASs, looking at the interferences that are happening there, we look at the interferences happening across all of our IPv6 ASs. So the most striking observation for us here is the removal of TCP extensions. And we find that these contribute over 40% to all of the interferences. And this then again goes to what I mentioned at the beginning of this talk, that middle boxes tend to resist extensions and also new protocols. Now we find that nearly 13% of these IPs, highest confidence IPs, happen to be present in IPv6 tier 1s. But the situation is not as bad as in IPv4, where nearly double that fraction are in tier 1s. Now to further drive this point across, that IPv6 the situation is not as bad, we find that in all of our IPv6 measurements, even the geographically distributed ones, the percentage of middle box affected parts never touches 1%, whereas for IPv4, this is much higher. So this then means that these path-breaking TCP extension resisting middle boxes, which we have seen previously in the IPv4 internet, also tend to exist in the IPv6 internet, but there is a much lower path brokenness in the IPv6 internet. Then I'll end with this final slide. So thus far, the analysis has been on IPs, highest confidence IPs, but it's quite possible that multiple such IPs could be present on the same device. So this is what we try to do this with alias with alias resolution here. So we look at, so for this alias resolution, we use the SNMP-v3 dataset. The dataset sends unsolicited SNMP-v3 packets to info aliases, and the dataset has IPv4 alias sets, IPv6 alias sets, and also dual stack ones. It also contains singleton as well as non-singleton alias sets. So what we do is that we combine highest confidence mailbox IPs from all of our scans, and then we look for them in this dataset. We find that we map over 11% of these IPs to the dataset, and the majority of these map to non-singleton sets therein. By doing this, we are able to find about 132 non-singleton or multiple alias middle boxes, 20% of which we find to also be dual stack. Finally, the dataset also allows us to see vendor information. And we find that nearly more than half of these devices, singleton as well as the non-singleton middle boxes, happen to come from Cisco. The other 20% then come from Juniper, and this then already shows that these middle box devices tend to come from a much lower concentration of vendors. With that, I've reached the end of the talk, but I'll finish with a very quick summary of what I talked about. So I started off with talking about Tracebox and how it's not ideal for large-scale large-scale internet studies based on middle boxes, and how we fix this, address this with our tool Yarrpbox, which is a high-speed, low distributed middle box detector, which we then also leverage to perform measurements in the IPv4 and the IPv6 internet. And we find that the tool works out quite well in the internet because this is what we see from our traces, which happen to be complete for the most part. Finally, we also uncover a much lower prevalence of these path-breaking middle boxes in the IPv6 internet, which have been plaguing the IPv4 internet now for quite a while. And with that, the artifacts are public, and I'll also be speaking about them later on. So if you're interested, you could join there as well. And with that, I thank you, and now I'll be happy to take your questions.
Okay, questions for Fahad?
Thanks for that. Andrew Moore from Cambridge. So can I just clarify something on this one? So the TCP checksum change implies that it's doing payload manipulation. Is that right?
I'm sorry?
The TCP checksum change, this illegal change, implies a payload manipulation. Was that right?
No, we find these changes to happen without any alterations anywhere in the header, which is quite strange.
Okay. The other one was, like always, these things, the measurements are the most revealing. What is the takeaway from the impact of new protocols running on top of old ones, such as the internet has become quick on top of on top of TCP, on top of UDP, so you're just never going to see some of that stuff. Did you get any insights for the new transport protocols?
So we did not use QUIC or any of those new protocols. We mainly worked with TCP and UDP. So these are measurements mostly at the transport layer, but we did not look at QUIC. Maybe in the future.
Hello. Right. So you mentioned that it's not always possible to determine the exact IP because of how traceroute works, and this system as well. Would it be an option to sort of narrow down the exact IP by measuring from two opposing ends, basically trying to measure from the source and from the
I'm sorry, could you repeat the question? I was not able to locate you.
Oh, sorry. Okay, so my question is referring to the problem of determining the exact IP, because you mentioned that when you perform the traceroute or the Yarrpbox trace, that at some point, if there's a gap, you can't determine whether that's where modifications were made or if it's at some later point, and whether it would be an option to measure from two ends to determine the exact IP, whether that would be an option to narrow it down further. So
if I understand the question correctly, you mean would it be helpful if we could do the measurements from both ends?
Yes, basically.
I mean, it could be, but the internet paths, are asymmetric and you cannot predict what's going on. But maybe it could be something that we could test as well.
Okay, thank you.
Hi, thank you for the great talk. I'm right here, if you can't find me. But so you mentioned there's some sort of relationship between, relationship between the ASs and the amount of interference that was happening in them. Did you also look at something at the country level? Because I was trying to find reasons for why some of these mailboxes would do such interference, and maybe if censorship was one of the reasons that you kind of is there some sort of a relationship between where the Middleboxes are, for example, in countries like China or India, where you expect censorship to happen, and these interference events?
So we did not perform the measurement. We do not look at a country level, but we did find some Middleboxes in China, which were altering weirdly the payload length in the packets. They were setting those to very, very high values in excess of 17,000 bytes. I'm not sure if that is something that might be related to censorship, but we did not.
Yeah, there's a bunch of stuff that looks at internet Middleboxes and how they mess up your packets if they're trying to censor you. So maybe we can talk about it later on. Thank you.
I have more questions. I have a very naive question probably for you. So it's a tool. It's a very nice tool. It's stateless, right? There's all nice features. But how did vision is being used? Who's going to use it and to detect what kind of Middleboxes?
Well, Middleboxes that rewrite packets and do these sorts of weird things like TCP section modifications. So basically, protocol designers who are sort of interested in Middlebox deployments or interested in creating and innovating and creating new protocols, basically. Also, you can use it to maybe debug networks to see what is going on, why your packet is not going past the port hop with the MPTCP, for instance.
Okay. Okay, so let's thank again Fahad for the presentation.
Thanks for the introduction. So I'm Vipul, and I'm going to talk about FLOC, which is a system for accurate network fault localization for large-scale data center networks. So this is joint work with Tong Meng, Kapil Agrawal, and my advisor, Brighton Godfrey, at University of Illinois, Urbana-Champaign. So data center network failures are pretty common, and they cause a lot of performance issues and network downtime. But the trickiest failures are those which are not even reported by the system, and these are known as gray failures. So some examples of gray failures are links or devices, which could be silently dropping packets without updating the packet counters, or maybe some subtle configuration errors, which can affect a small fraction of the packets. And since these failures are not caught by the failure detectors of the system, we have to rely on end-to-end measurements from the host to catch these gray failures. And there could also be other advantages of using end-to-end measurements to catch these failures, such as maybe there are a lot of alerts in the system and we want to find the root cause of a specific incident, or maybe we just want to cross-check a fault that's already been reported. All right. So our goal is to localize faults in data center networks using end-to-end measurements from the host. And these measurements include flow metrics that the host can see. So for example, packets sent, retransmissions, the number of packets dropped, or the latency of the flow. And we also assume the topology of the data center. And we want the fault localization scheme to be accurate because that translates directly to the amount of human effort that's required for mitigating that failure. And we also want the fault localization scheme to finish reasonably quickly because any time that's lost in localization is network downtime, essentially. And we present FLOC, which is a fault localization system for data centers, which achieves dramatically higher accuracy and speed than previous works. Okay, so before I describe FLOC, let me describe a typical workflow for how a fault localization system can be. So hosts have agents which are running on them, and these agents collect and send flow reports to a logically centralized collector, and this collector takes all those flow reports and using the network topology invokes an inference engine. And this inference engine will then run some sort of analysis and output a list of failed links or devices. So in this workflow, we can categorize previous works along two axes. So the first axis is okay. So the first axis is what flow reports are collected by the agent. And there are two types of flow reports that can be collected. So the first one comes from the agent sending out active probes to the network to gather measurements, and then it reports the metrics of those probes. And the advantage here is that the agents can control where the probes go. They can control the path of the probes and so on. But the disadvantage is that they can only send a limited number of these probes, and these probes might also take a different data path than the actual traffic. So the second kind of flow reports comes from passively observing the actual traffic in the data center, and this monitoring data is very voluminous in nature, since there's a lot of flows in the data center. But it's also tricky to incorporate for fault localization because it can be highly irregular, and you further might not even know the path that was taken by these flows, depending on what kind of monitoring you have. The second axis along which we classify fault localization systems is based on the inference technique. So the first set of systems use a technique known as a probabilistic graphical model, and this technique is been known to work is known to be very accurate in practice. But it's the problem with this is that it's interactably slow at scale. And so Sherlock is a system which uses PGM, but the context in Sherlock is only it only has like hundreds of components in the system that they were testing, whereas a data center might have like 2-3 orders of magnitude more components. And because of this interactability, all data center fault localization schemes move away from PGM-based techniques and utilize some heuristics or other algorithms, which are pretty fast, but they sacrifice the accuracy or the flexibility that PGMs offer. Now, if we could solve the scalability challenges with PGMs, that would be very handy because data center networks experience a lot of failures, and because PGMs are very accurate, then we can conduct highly accurate fault localization if we could do that. So with those ideas in mind, we created this system Flock, which is based on PGMs. But to deal with the scale of the data center, we designed new and faster algorithms for discrete valued PGMs. And because PGMs are flexible enough, and this flexibility allows Flock to utilize both active probes and passive monitoring. And this is just a happy consequence of using PGMs. So we can take advantage of whatever is available. Okay, so I'm going to give you a very brief overview of the kind of PGMs that we're going to use. So we're going to use what's known as a Bayesian network. So these are PGMs that are based on an acyclic graph, and each node is a random variable in this graph, where if you know the value of ancestors of a node, then you can completely determine the distribution of that node. So this is known as conditional independence. And just to illustrate this point, maybe you are a person whose happiness depends on the conditions of sun and rain in the environment, but those things in turn depend on a lot of other external factors, like let's say North Pole wind or something. And but if you know the value of sun and rain, then you don't care about those external factors. So it boils down to, given the value of sun and rain, your happiness is independent of external factors, which are not your immediate ancestors. So those are the things that these Bayesian networks can capture. And how can we use this for inference? So typically, you have these internal system variables, and the PGM, and then you also have the observed variables, which are on the bottom layer in this graph. And the PGM allows us to predict the observed variables given the internal system variables. But the inference problem is actually the flipped one, where we see the observed variables, but we want to figure out what the unknown internal variables are. And you can see, like here, I'm showing you 3 internal variables. And if those are like binary valued, then you have an exponential number of choices to figure that out from. So that's where the interactability comes from. Okay, so let's dive deeper into how Flock uses this for fault localization. So the first step is to construct the PGM graph for the data center topology. So I'm going to show you a toy example here. So let's say you have a physical network that looks like this, and you have a flow that for which you have 2 paths that are available to that flow, and it gets randomly routed on one of those. But you don't know which one. And for the corresponding PGM is like a 3-layer DAG, where the top layer of nodes are the link represent the links or devices, and these are the unknown variables. So basically, the unknown is the failed, not failed status of that link. So if it's a 0 if that link is correctly working, and 1 if it's not working, and that's what we want to infer. The intermediate layer represents the paths for that flow, and then you have the flow nodes, which are your observed variables, basically the metrics of that flow. And if you have another flow, then you can also add the corresponding nodes in the PGM graph for that. Okay, so that was a toy example. Here is just a slightly larger toy example with 100 servers and 500 flows. But you can imagine that with a data center with hundreds of thousands of components and millions of flows, which is pretty common, this is going to be a huge PGM, and inference and running inference over it is going to pose a huge scalability challenge. Okay, so the second part is to define the relationship between the unknown variables and the observed variables in this PGM. Recall that the unknown variables are the status of each link. So let's say we begin with some assignment, which is equivalent to saying which links have failed and which links have not failed. So we refer to this as a candidate hypothesis. So in this candidate hypothesis, L1 has failed and the other links have not failed. So let's see how the observed variables depend on this candidate hypothesis. So L1 has failed according to this hypothesis. We classify a path as having failed if it consists any of the any failed links. So in this case, P1 consists of L1, so we classify P1 as also having failed. And then you have the observed variables. So let's say for flow F1, you experience some 10 out of 1,000 packets that got dropped. So you can just write out the probability, assuming that you have some sort of random routing between the possible paths for F1, and then you have a certain drop rate associated with a failed link and a certain drop rate associated with a correctly functioning link, which is to model like some noise, because some packets can get dropped even on good links, maybe of congestion or some other cases. Okay, and then if we multiply all those probabilities for each flow, we get a way to score a hypothesis. Okay, so this gives us a way to evaluate a candidate set of failed links. Okay, so how do we infer the unknown variables? And the standard estimator that we'll be using, or that we want to use, is known as the maximum likelihood estimator, and this is basically trying to find out the hypothesis that maximizes the likelihood of seeing the observed variables, the metrics of the flows. But this is an exponential space, as you can see, and the existing algorithms to search this space are like brute force or MCMC or Gibbs sampling, but all of them are pretty slow for our for the data center scale. So the first idea is to sort of greedily find the set of failed links, one at a time. So we start out with the no failure hypothesis. So none of the links or devices have failed in this hypothesis, and we evaluate that using the model that I showed. And then in the second iteration, we extend the set of failed links by adding one more link to that set. And we move to the hypothesis that gives us the largest increase in the likelihood. So here it's the second one, and then again we added a second time, we try to extend by adding one more failed link, move to the one that gives us the highest increase in likelihood. And then again, when we do it for the third time, we realize that the likelihood would decrease on adding another failed link to the set of failed links. So this is the stopping criteria of the greedy algorithm. Now, the algorithm is simple enough, but the tricky part is to show that this algorithm is optimal if you have a large enough difference between the drop rates on a good link and the drop rates on a bad link. So that proof is in the paper. So please check that out if you want to. Okay, so it turns out that actually even this greedy is too slow, and the reason is that we have the data center has lots of components, and in every iteration you are trying to evaluate n hypotheses in the greedy algorithm, and each of those hypotheses might potentially involve millions of flows. And on a large multi-core machine, this took about 30 minutes, and that's a lot of network downtime already caused because of the runtime. So we want to reduce that even further. And this is where our second idea comes into picture. We refer to this as joint likelihood exploration. And this is an acceleration technique. So the idea is to maintain an array of hypotheses that we can update all at once to evaluate a set of new but similar hypotheses. So the insight is that that turns out to be cheaper than evaluating each of them one by one. And this acceleration technique gave a speed up of about 100x for greedy, but there's nothing special about greedy. It can also accelerate other standard algorithms like MCMC, Gibbs sampling, or brute force. So I'm just going to give a very high level idea of this, but all the details are in the paper, of course. So like in the greedy algorithm, we start with the no failure hypothesis. We compute the likelihood for that. And then in the second case, when we want to evaluate all of these neighbor hypotheses, where we flip the status of a single link or a single device, instead of evaluating them from scratch, what we do is store the differences between all of these hypotheses and the current hypothesis of the greedy algorithm. So here we have an array, the delta array, and if we know the differences, then we can easily figure out where to go next. It's just a linear scan. But when we update the greedy, when the greedy algorithm updates the current hypothesis, it moves to a new hypothesis. We need to update this difference array with respect to the current hypothesis, which we updated. And the idea is that if we take the difference between the likelihoods of successive iterations between the hypothesis in successive iterations, the difference is large. But if we keep track of the difference of the differences between iterations, that difference turns out to be computationally more efficient to compute. So we exploit that, and we essentially gain a factor of n over d improvement in running time. So where n is the number of links, d is the maximum degree in the graph. So that's pretty significant. Okay, so I'll move to evaluation. First I'll describe the types of input flow reports that we feed to the fault localization system. So the first one comes from the agents sending out active probes to the network to gather measurements, and these active probes are uniformly sent across the network, across the data center. And we know exactly where these probes are going. So we know the path for these probes. The second set of flow reports comes from trace routing application flows, where we send out a trace route with the exact same 5-tuple so that it takes the same path as the application flow. And then we, using that method, we are able to find out the path of those flows. The third one, constitutes the vast majority of the actual traffic, where we only know the end-to-end metrics for the flows, but we do not know the paths that was taken by those flows. But using the topology, we can figure out, the possible set of paths that these flows could have taken, but we don't know the exact path. And finally, we also experiment with some advanced telemetry, such as, if you have in-band network telemetry or programmable switches, you can stamp every packet at every switch, and that gives us a method to calculate the path for every flow. All right, so we'll test, we'll run our experiments with the combination of these. Okay, so this is our setup. We experimented with the standard data center topologies, 2-tier, 3-tier. We injected failures to these topologies and collected all kinds of flow reports that we collected, and then we have multiple baselines, a net bouncer in 007, the non-PGM data center fault localization schemes, and also another baseline scheme that you can't see. Okay, so how do these schemes trade off between precision and recall? So precision and recall are like the standard ways to measure false positives and false negatives. And for every scheme, we have these hyperparameters, which if we play with the hyperparameters, maybe we get better precision, but at the cost of lower recall. So just by playing with the hyperparameters, we kind of get a trade-off curve between precision and recall. And what we are really looking at here is schemes that are to the upper right, because those schemes will represent high precision and high recall. Okay, so these are all the schemes that we tried, and you can see flock pretty much gets with some settings of hyperparameters, it gets in the upper right corner of this plot, and it achieves high accuracy compared to all the baselines. So this is so this failure scenario is silent packet drops. This is a scenario where we misconfigured a queue threshold, the threshold above which a packet will get dropped on that queue. And here also you can see the flock schemes are on the upper right, whereas the baseline schemes have significantly poorer accuracy. The second scenario we tried was a link flap. So in this failure, we quickly took out a link and put it back in quickly. And this is to emulate transient downtimes that a link might experience. So this also occurs in data centers. And here also you can see that the flock schemes are to the upper right. Okay, so how does how fast is flock? So if we compare it to previous PGMs, Sherlock is one such system. So if we have two different optimizations, greedy and the joint likelihood exploration, JLE, and each of those techniques gives us like a 100x improvement over Sherlock. And when we combine them, the overall speed improvement is about 10,000x, which allows flock to use a PGM at scale. So how does flock compare to other data center schemes, data center fault localization schemes? Flock is reasonably fast. It takes about tens of seconds for a reasonably sized data center, which is not so bad. In fact, it's even faster than some of the non-PGM methods, which were trying to avoid the runtime issue with PGMs. All right, so I'll conclude here. Please check out our paper for more details. We have the entire algorithm along with the proofs. We also have a lot more experiments. We test how robust our scheme is to imperfect data. What if you only have passive input, device failures, and other kinds of failures. So that's it. Thank you, and I'm happy to take questions.
Thank you for the interesting talk. You were hinting at the fact that the greedy algorithm always finds the optimal solution. Can you give an intuition as to why that would hold up? Why you don't have to consider any scenario where the previously selected optimal link failure always leads to the perfect?
So that depends on, so there are certain conditions under which that is true, and that's mostly true for most, practical cases. So the condition is that there should be a large, if there is a large gap between the drop rates on the failed link and on a good link, then if the gap is not large, then the algorithm can get confused and what you're saying might happen. But if there is a large enough gap, then that does not happen. So that's the condition. But in general, yeah, you're right. It won't work for any PGM out of the box.
And we have a question up there.
Yeah. So it's here. Oh, it's over here. So thank you for the presentation. I have two questions. And the first goes to the overhead. So how would you comment or on the the amount of data you have to collect?
Sorry, can you speak up, please?
Yeah, sorry, I'll do that again. So
Yeah.
I have two questions actually. The first goes to the overhead. The overhead in terms of the amount of data you collect and also the amount of computation that you get to reason about it. And the second question goes to, I look at the failure cases you're thinking about. It goes perfectly fine to those kind of a single point or a failure being localized to a very specific point. So how about those failures or bugs having some commonality across multiple nodes? Would I be able to find them as well? For example, it could be some just bugs in the middleware or firmware that could be triggered by a specific set of traffic.
Right.
Yeah,
So,
please.
okay. So the first question was, what's the overhead of the monitoring data? So, I mean, the kind of input flow reports that we assumed is basically taken from, some papers from the industry where they're actually using collecting, sending out active probes and collecting that data. So we just, we are just saying, just use our inference engine instead of yours, and you'll get a better answer. If the volume is too large, you can always downsample it randomly, and you can run the analysis with the sampled monitoring data. So this is essentially, I mean, I would say that this is more of an engineering challenge, and most people we've talked to in the industry, they do have they collect some sort of monitoring data already, and they can just take our algorithm and run it. The second question was, what if the failure is in a different layer? Well, we only handle network failures, so we'll localize the failure to a device or a network component, and thereafter the network operator can examine that device and figure out what's wrong with it. Does that answer your question? Thanks.
Okay, Andrew.
So my experience of network operations people is they hate probabilistic tools. So are you able to put some confidence boundaries on these things? Because otherwise they tend to get turned off.
So that's a good question. I mean, they will get turned off if there's a lot of false positives. I mean, if often the fault localization system is reporting a failure, but that's not useful to the operator because it's often a false positive. Well, some of the baseline schemes that we have experimented with are actually in use in the industry in some ways, or were at some point. So I mean, the answer to that is, I mean, I don't have real deployment experience with the system, so I can't say for sure. But if at least I can say that if a baseline scheme was being used, then I have some certain degree of confidence that if you use our PGM based methods, then maybe you'll get a better result. I mean, that's a hard problem. I mean, not as yet, but maybe that's an open problem we can look into. Yeah.
Or maybe just a short follow-up to what Andrew asked. So it's not about your paper, but in general data set and networking, like in-based congestion control or other work. It's pretty much all by simulations. So your personal reaction, I know, do you find it frustrating? Do you ask yourself, is it real, whatever I propose or whatever other people who publish papers on the topic?
I mean, this is like a deep philosophical question. So essentially, a lot of academic papers, don't have the resources for, having that real deployment experience. What we did was we did try it on our testbed setup with like a much smaller setup. We were able to validate that, whatever we're seeing in simulation at that small scale, we also reproduced it in the testbed. So that gives us some confidence that, the larger scale results will also hold to some degree. But, of course, we don't have a real data center to test with. So we are at a loss. Maybe if people in the industry released more open source traces, then that would be very helpful for sure.
Okay.
Yeah.
Well, I learned one thing, that North Polar winds are responsible for my happiness and unhappiness. But I guess we have no time for philosophical or technical questions anymore. So let's thanks once again all the speakers and Hilal again.
Thank you.